Tonight, the moon turns its hidden face towards silence. No human being has ever stood on that far side and looked back at Earth with the same familiar sky above. What astronauts and lunar missions uncovered there was not empty darkness, but a landscape so ancient, so isolated, and so strange that it changed the way science understands the moon forever. Craters deeper than mountains are tall, signals cut off behind solid rock, and clues from the earliest solar system remain locked in shadow. Before the journey begins, please like the video, subscribe to the channel, and stay with the story as the far side slowly comes into view. A wide region extends between Earth and the Moon, a span often called cislunar space. It is not empty in an absolute sense, yet it contains so little matter that distance becomes the dominant presence. Particles drift sparsely, mostly single atoms of hydrogen and helium carried outward by the solar wind. A steady flow of charged particles from the Sun. The density here is extremely low, far below the thinnest laboratory vacuum achieved on Earth. Matter exists as scattered traces, while radiation moves freely without obstruction. This environment defines every journey toward the far side of the Moon. Spacecraft leaving Earth pass through layers that gradually thin from the upper atmosphere into near vacuum. Once beyond the outer reaches of Earth's atmosphere, the craft enters a region where air no longer carries heat or sound. Temperature is not felt in the same way as on Earth, because there is no surrounding medium to conduct warmth. Instead, surfaces gain or lose heat through radiation alone. A surface facing the Sun absorbs energy and warms, while a surface facing darkness loses energy and cools. The difference between these conditions can be extreme, yet it depends entirely on exposure. Radiation becomes a defining factor in this region. Without the protection of a thick atmosphere or strong magnetic field, high-energy particles from the Sun and beyond move freely. These include protons and heavier ions, as well as electromagnetic radiation such as ultraviolet and X-rays. Spacecraft and astronauts must rely on shielding to reduce exposure. Observations indicate that the intensity of this radiation varies with solar activity. During periods of calm, the flux is steady and moderate, while during solar events it can increase sharply. It remains uncertain how smaller fluctuations over long durations may influence material fatigue in spacecraft structures. Gravity still acts across this distance, shaping motion in a subtle but constant way. Earth's gravitational pull weakens with distance, while the Moon's pull grows stronger as one approaches. Between them lies a region where these forces balance in complex patterns. Spacecraft follow curved paths influenced by both bodies, guided by precise calculations. These paths are not straight lines but arcs that reflect the invisible contours of gravitational fields. The journey across this region takes several days using conventional propulsion. During this time, Earth gradually recedes, shrinking from a large sphere to a smaller disk against the black background. Its atmosphere appears as a thin, bright line at the edge, scattering sunlight. Clouds shift slowly across continents and oceans, but from increasing distance, these details merge into patterns of light and colour. The Moon, in contrast, grows from a distant point into a distinct sphere marked by light and dark regions. Silence defines the environment. Sound cannot travel through vacuum, as it requires a medium such as air or water. Inside a spacecraft, mechanical systems produce vibrations and noise, but outside, motion occurs without audible trace. Objects move in quiet arcs, and impacts release energy without sound. This absence of sound alters perception, leaving visual and instrumental data as the primary sources of awareness. Micrometeoroids pass through this region as well. These are tiny fragments of rock and metal, often smaller than grains of sand. Travelling at high speeds, their origins lie in asteroid collisions and comet debris. Even at small sizes, their velocity allows them to carry significant kinetic energy. Spacecraft surfaces are designed to withstand such impacts, often using layered shielding. Observations show that most particles are extremely small, but occasional larger fragments can pose a greater risk. It remains uncertain how frequently such impacts occur for extended missions, though accumulated data provides general estimates. The solar wind interacts weakly with spacecraft materials, gradually altering exposed surfaces. Over time, this process can cause slight erosion or changes in the electrical charge. Electrostatic effects become relevant, as surfaces can accumulate charge when exposed to sunlight or shadow. These charges may influence fine dust behavior once near a planetary surface, though in open space they remain subtle. Light behaves in a clear and direct manner in this region. Without atmosphere, there is no scattering to soften shadows or diffuse brightness. Sunlit surfaces appear sharply defined, while shaded areas fall into deep darkness. The contrast between light and shadow is pronounced. Instruments must adjust to this range, capturing detail without losing clarity. As the spacecraft continues outward, Earth's influence diminishes and the Moon's presence becomes more prominent. The transition is gradual but measurable through navigation data. The gravitational center of motion shifts, and trajectories adjust accordingly. The spacecraft aligns with a path that will bring it into lunar orbit. Throughout this journey, communication with Earth remains constant. Radio signals travel at the speed of light, crossing the distance in just over 1 second. This delay is noticeable but manageable. Signals carry data, images, and measurements, forming a continuous link between spacecraft and mission control. This connection persists until the spacecraft approaches the far side of the Moon, where direct line of sight will soon be interrupted. The far side remains hidden during this approach. From Earth, it cannot be seen due to the Moon's rotation being synchronized with its orbit, a state known as tidal locking. This means the same hemisphere always faces Earth, while the opposite hemisphere remains out of direct view. Spacecraft approaching the Moon from this trajectory will eventually pass beyond the line where Earth is visible, entering a region where communication must rely on relays or be temporarily lost. In this outer region, anticipation is shaped by physical reality rather than perception. There is no sudden boundary marking the beginning of the far side. Instead, geometry defines visibility. As the spacecraft moves along its path, Earth slowly approaches the edge of the lunar disk from the spacecraft's perspective. At a certain point, it disappears behind the Moon entirely. This moment marks entry into a zone where Earth-based observation cannot directly reach. Observations indicate that this transition has practical consequences. Radio silence can occur when a spacecraft moves behind the Moon, unless relay systems are in place. During early missions, this period was brief but significant, requiring careful planning. It remains uncertain how continuous human presence on the far side would manage communication without extensive infrastructure. The journey across cislunar space thus establishes the conditions that shape all exploration beyond Earth. It is defined by vacuum, radiation, gravitational balance, and silence. These elements do not change suddenly but persist as steady influences. They form the outermost layer of the path toward the far side of the Moon, setting the stage for what lies closer to its surface. The Moon moves around Earth in a way that creates a stable visual pattern. From Earth, one hemisphere remains in view while the other stays out of direct sight. This is not because the Moon does not rotate, it does rotate, but it does so at nearly the same rate that it completes one orbit around Earth. One full turn on its axis takes about the same amount of time as one full trip around Earth. Because these periods closely match, the same general face remains turned toward Earth. This condition is called tidal locking. It is the result of gravitational interaction over a very long span of time. Gravity acts unevenly across a body when another massive body lies nearby. The side of the Moon closer to Earth feels a slightly stronger pull than the side farther away. Early in lunar history, when the Moon likely rotated at a different rate, this uneven pull raised tidal distortions in its solid body. Those distortions did not align perfectly with the Earth-Moon line. Internal friction then converted rotational energy into heat and gradually slowed the Moon's spin until a stable state was reached. In that state, the Moon's rotation and orbital period became closely matched. The process is well supported by physics and by observations of other moons in the solar system that show similar behavior. This locked motion creates the distinction between the near side and the far side. The near side is the hemisphere that faces Earth most of the time. The far side is the hemisphere that faces away most of the time. These names describe position, not light. The far side is not permanently dark. It receives sunlight just as the near side does. Day and night pass across both hemispheres over the course of the lunar cycle. Each location on the Moon experiences roughly 2 weeks of daylight followed by roughly 2 weeks of darkness. The hidden quality of the far side comes from geometry alone. The Moon's orbit is not a perfect circle, and its rotation is not viewed from a perfectly fixed angle. Because of this, small variations occur in what can be seen from Earth over time. These variations are called librations, meaning slight apparent oscillations. They allow observers on Earth to glimpse a little more than half of the lunar surface across many cycles, though never all at once. In total, about 59% of the Moon becomes visible over time from Earth. Even with this shifting view, the central regions of the far side remain hidden from direct Earth-based observation. For much of human history, the far side remained an unseen hemisphere in the strictest sense. Telescopes improved the detail of the near side, revealing plains, mountains, and cratered highlands, but they could not overcome the geometry of the locked orbit. Maps of the near side grew increasingly precise, while the hidden hemisphere remained unknown. This separation shaped ideas about the Moon for centuries. The visible face became familiar. The far side remained a blank area in maps and imagination until spacecraft finally passed beyond the visible limb. The hidden hemisphere differs from the near side in important ways. This difference is not evident from Earth, because the near side dominates all ordinary viewing. Once spacecraft begin to orbit the Moon, the full globe can be mapped. Those maps reveal that the far side has far fewer broad dark plains than the near side. The near side contains many maria, a term for ancient basalt plains formed when lava flooded large basins. The far side is dominated more strongly by brighter, heavily cratered highlands. The overall contrast between hemispheres becomes one of the most striking large-scale features of the Moon. The locked relationship between Earth and Moon also creates a special radio environment on the far side. Radio waves from Earth travel outward into space and can reflect, scatter, or weaken depending on frequency and local conditions. On the near side of the Moon, Earth remains above or near the horizon depending on location, and human-made radio emissions are always present in some form. On the far side, the bulk of the Moon itself blocks direct radio signals from Earth over a broad range of frequencies. This produces a region of natural radio quiet. That shielding matters because modern civilization fills nearby space with radio noise. Broadcast systems, radar, satellite communications, and many other technologies create a dense pattern of artificial signals around Earth. These signals can interfere with sensitive attempts to detect faint natural radio emissions from the cosmos. The far side of the Moon offers protection from much of that interference. Observations and engineering studies indicate that this makes it one of the quietest accessible places for certain forms of radio astronomy, especially at long wavelengths that are difficult to study from Earth's surface. Earth's ionosphere, a charged upper layer of the atmosphere, blocks or distorts some of these low-frequency signals. The far side avoids both much of the Earth-made noise and the masking effect of the atmosphere. This radio silence has practical consequences beyond astronomy. A spacecraft on the far side cannot usually maintain direct contact with Earth unless another spacecraft or relay station provides a communication link. During lunar orbit, vehicles pass behind the Moon and enter temporary loss of signal. This has been a routine part of many missions. The interruption is expected and precisely timed. During the Apollo era, crews experienced these intervals whenever they moved behind the Moon. The silence was not mysterious. It followed directly from line-of-sight geometry and the blocking effect of solid rock. A similar principle applies to navigation and command. Earth-based control depends on radio contact. When that contact is lost, systems must operate independently for a time or rely on pre-planned instructions. Modern missions to the far side often use dedicated relay satellites placed in positions where they can see both Earth and the hidden hemisphere. Such arrangements make continuous communication possible, but only through added infrastructure. Without that support, the far side remains physically and operationally separated from Earth. The hidden hemisphere is therefore not only a different face of the Moon, it is a different observational domain. Earth disappears below the horizon or never rises at all from many locations there. The planet that dominates the near-side sky is absent. Direct radio contact is lost. The sense of connection changes because the largest nearby body in lunar experience no longer appears overhead. Instead, the Moon itself becomes the shield. This distinction has scientific value because shielding allows a cleaner environment for measurement. It also has historical value because the far side remained unseen until the space age, when the first spacecraft finally returned images of that hemisphere. The results did not reveal anything supernatural or monstrous. They revealed terrain shaped by impact, crustal history, and deep time. What appears at first as concealment proves to be a simple consequence of orbital mechanics. The Moon keeps one face toward Earth because gravity has steadily arranged it that way. The far side remains hidden not by intention or mystery, but by a slow balance reached long ago and maintained ever since. Above the far side of the Moon, the sky presents itself without the familiar presence of Earth. The field of view is defined instead by the Sun, the distant stars, and the slow turning of the lunar surface beneath. The absence of atmosphere means that nothing scatters light. The sky remains black even when the sun is high. This condition differs from Earth, where air molecules and particles diffuse sunlight and create a blue sky. On the Moon, the lack of air allows light to travel directly from its source to any surface it strikes, leaving the rest of the sky in darkness. Sunlight arrives unfiltered, carrying its full intensity across the vacuum. Surfaces that face the sun become bright and sharply defined. Edges cast clear shadows that extend across the ground without gradual fading. These shadows appear deep and uniform, because there is no surrounding light to soften them. Observations from lunar orbit show that this contrast between brightness and darkness can be difficult for instruments to balance. Cameras must adjust carefully to capture both illuminated areas and shadowed regions without losing detail. The sun appears slightly smaller than it does from Earth due to the greater distance from its surface to the observer. This difference is subtle and does not alter its brightness in a noticeable way. The solar disk remains intense, and direct exposure can raise the temperature of exposed materials significantly. When the sun moves across the sky during the long lunar day, it traces a slow path. One complete cycle of daylight and darkness lasts about 1 lunar month, which is roughly 29 Earth days. Each location experiences about 2 weeks of continuous sunlight followed by about 2 weeks of night. During the period of darkness, the sky becomes even more defined by distant light sources. Stars appear steady without the twinkling seen from Earth. Twinkling arises from turbulence in the atmosphere, which shifts the path of light slightly as it passes through layers of air. In the absence of atmosphere, starlight travels in straight lines. Points of light remain fixed and clear. The Milky Way appears as a faint band of countless stars, more distinct than when viewed through air. Planets also become visible as bright points moving slowly against the background of stars. Their motion reflects their own orbits around the Sun, observed from the changing position of the Moon. Without atmospheric distortion, their light remains steady. Instruments can measure their brightness and position with high precision under these conditions. On the far side, Earth does not rise above the horizon in the way it does on the near side. From most far-side locations, Earth remains permanently below the horizon. Only in regions near the boundary between the near and far sides might a small portion of Earth appear briefly due to libration. For the central far side, however, Earth is absent from the sky. This absence removes a major source of reflected light. On the near side, Earthlight can illuminate the lunar surface faintly during the lunar night. This is light reflected from Earth onto the Moon. On the far side, that effect is largely missing. The darkness becomes more complete. The lack of Earthlight influences both observation and temperature. Surfaces in shadow receive almost no illumination except from distant stars, which contribute very little energy. As a result, temperatures can fall to very low values during the lunar night. Measurements from previous missions show that temperatures can drop far below freezing, reaching levels where most materials become extremely brittle. During the day, the same surfaces can heat to high temperatures when exposed to direct sunlight. This wide range results from the absence of atmosphere and the slow rotation of the Moon. The horizon appears closer than on Earth because the Moon is smaller. Its radius is about 1/4 that of Earth. This curvature means that the surface drops away more quickly from any given point. Standing on the surface, the visible distance is shorter. Mountains and crater rims can block the view, creating enclosed basins where the sky is partially hidden by terrain. From orbit, however, the full curvature becomes visible as the spacecraft moves above the surface. Light reflecting from the lunar surface has a distinct quality. The ground is composed largely of fine particles and broken rock. These materials scatter light in ways that produce a soft brightness when viewed from certain angles. The reflectivity, known as albedo, varies across the surface. The far side generally appears brighter than the near side because it contains fewer dark basalt plains. This brightness is not uniform. It changes with the angle of sunlight and the texture of the surface. The terminator, the line dividing day and night, moves slowly across the far side. Along this boundary, shadows stretch long across the terrain, revealing details in relief. Crater rims, ridges, and slopes become more visible due to the low angle of sunlight. This region provides valuable conditions for observation, as subtle features stand out more clearly. As the sun rises higher, these shadows shorten and the contrast decreases. radiation continues to pass through this region of space above the far side. Without Earth's magnetic field, the Moon offers little protection from high-energy particles. The lunar surface itself can absorb or scatter some radiation, but above it, the exposure remains direct. Instruments in orbit measure this radiation to understand its variation over time. Observations indicate that the far side experiences similar radiation conditions to the near side when exposed to the same solar environment. The difference lies not in the radiation itself, but in the absence of Earth's influence. The radio environment remains notably quiet. With the Moon blocking direct signals from Earth, the far side sky becomes a place where natural radio emissions can be observed with less interference. These emissions include signals from the Sun, distant galaxies, and other astrophysical sources. Instruments designed to detect such signals benefit from the shielding effect of the lunar body. This quietness does not imply a total absence of radio waves. Natural sources still contribute, and some signals can diffract around the lunar limb. However, the overall level of human-made interference is greatly reduced. As a spacecraft orbits above this hemisphere, it alternates between regions where Earth is visible and regions where it is hidden. During the hidden phase, communication must rely on relay systems if continuous contact is required. The transition between these phases is gradual, following the curve of the Moon. Earth appears near the horizon, then slowly disappears behind the surface as the spacecraft moves along its path. The far side sky, therefore, is defined by clarity, contrast, and absence. It lacks the atmospheric effects that shape the sky on Earth. It lacks the constant presence of Earth itself. It presents a stable field of distant light sources against a deep black background. These conditions are not unusual within the context of space, yet they become distinct when tied to a surface where observation can take place over long periods. The environment above the far side sets the visual and physical context for everything that occurs on the ground below, where light and shadow will define the appearance of the terrain. Below the far side sky, the terrain rises into view as a broad expanse of rough high ground. From orbit, this hemisphere does not show the same pattern of wide dark plains that marks much of the near side. Instead, it appears brighter overall, more densely textured, and more heavily marked by impact. The dominant impression is one of old, elevated crust that has remained exposed for immense spans of time. The far side is not uniform, yet its large-scale character is defined by highlands, meaning ancient upland regions made largely of lighter rock and shaped by repeated collision. As a spacecraft descends in altitude, the broad texture resolves into overlapping circles, ridges, and uneven surfaces. Craters cover nearly every visible stretch of ground. Some are small and sharp-edged, while others are large and subdued, their rims softened by later impacts. Between them lie ridged plains, ejecta blankets, and broken slopes. Ejecta is the material thrown outward when an impact excavates the surface. It falls back in sheets and rays, covering nearby terrain with fragmented rock. Over time, new impacts strike old ejecta, and the surface becomes a layered record of collision upon collision. The far side highlands are older than most of the large volcanic plains on the near side. Their age is inferred from crater density. In planetary science, a surface with more craters is generally older because it has been exposed longer to bombardment. This method does not give an exact date from appearance alone, but it provides a strong relative sequence. By this measure, much of the far side preserves very ancient crust, dating back to the early history of the Moon. Observations from orbit and analysis of lunar samples linked to highland material indicate that these terrains formed early, soon after the Moon's crust solidified. The brightness of the highlands comes largely from their composition. They contain abundant anorthosite, a light-coloured rock rich in feldspar minerals. Feldspar is a group of minerals made mainly of aluminium, calcium, sodium, and silicon combined with oxygen. On the Moon, this rock is thought to have formed when a global or near-global magma ocean cooled in the distant past. Lighter minerals floated upward through the molten material and crystallized into a buoyant crust. The far side preserves much of that crust in exposed form. Later events altered it, but they did not erase its broad character. From above, the surface does not appear smooth even where it lacks large visible craters. This is because the highlands are saturated with impact features across many scales. A terrain is called crater-saturated when new impacts increasingly strike older craters instead of creating entirely fresh, unbroken ground. The result is a surface where the marks of collision overlap so densely that every part bears the imprint of previous events. In some areas, the landscape resembles a field of shallow bowls pressed into one another, interrupted by scattered peaks and broken ridges. Large basins add another level of structure. These are enormous impact features formed by collisions powerful enough to reshape regional crust. Their rims may stretch for hundreds of kilometers, though later impacts can make them difficult to recognize at first glance. Within and around these basins, the terrain often shows concentric rings, fractured blocks, and smoother interior zones. On the far side, many such structures remain more visibly tied to highland material because they were not as extensively flooded by later lava as many near-side basins were. The result is a stronger preservation of original impact forms. The descent over this terrain reveals strong differences in topography. Topography is the shape of the land, including height, slope, and surface relief. Far side elevations vary widely. Broad uplands stand higher than many near-side maria, and crater rims rise above surrounding plains. Central peaks appear within some larger craters. These peaks form when the lunar crust rebounds upward shortly after a major impact, much as a liquid surface briefly rises after being struck. Though in rock, the process is driven by shock and temporary weakening rather than fluid flow in the ordinary sense. The final landform freezes as the material cools and settles. Because there is no atmosphere, erosion by wind or water does not soften the landscape in the way it does on Earth. Slopes change slowly, mainly through impacts and the gradual downslope movement of loose debris. The sharpness of some crater rims and the preservation of ejecta patterns reflect this lack of weather in the earthly sense. At the same time, the surface is not static. Small impacts continue to break rock, mix material, and wear down fine details over very long timescales. The result is a terrain that preserves ancient forms while still undergoing constant slow alteration. The contrast with the near side becomes especially clear when one compares the abundance of maria. Maria are large, dark basalt plains formed by ancient volcanic eruptions that filled impact basins with lava. On the near side, they cover a significant fraction of the visible face. On the far side, they are fewer and generally smaller. The reasons involve crustal thickness, heat distribution, and volcanic history. But at the level of visible terrain, the outcome is direct. The far side looks more rugged, more elevated, and more uniformly ancient. Its highlands dominate the landscape from horizon to horizon. Orbital mapping confirms that the far side contains thicker crust on average than the near side. This thicker crust influences how deeply impacts excavate and how easily magma can later reach the surface. Although those internal processes lie below the terrain, their effects are visible from above in the persistent dominance of highland forms. The land itself becomes evidence of deeper structure. Observations indicate that the far-side crust resists volcanic flooding more often, allowing ancient impact landscapes to remain exposed rather than being buried under extensive basalt. Illumination strongly affects how this terrain appears. Under high sun, the surface can seem flatter because shadows shorten, and relief becomes harder to judge. Under low sun, crater rims cast long dark bands and subtle ridges stand out sharply. This changing appearance once complicated early interpretation of orbital photographs. Features that seemed like isolated mountains under one lighting angle could be recognized as crater walls under another. Careful mapping across different illumination conditions has been essential in understanding the true structure of the Farside Highlands. As the view moves lower still, the scale of the terrain becomes more apparent. What seems from high orbit like a slightly rough plain resolves into a complex field of slopes, boulders, and dusty hollows. There are few broad level expanses. Landing on the far side requires careful selection of safer zones within this broken topography. Even where the ground appears modestly smooth from orbit, smaller hazards may remain scattered across it. This practical difficulty reflects the scientific reality of the region. The far side is a place where ancient crust remains exposed, fractured, uplifted, and repeatedly struck. Its outermost landscape is the visible skin of long bombardment and early lunar formation, expressed most clearly in the battered highlands that dominate the descent. At the surface of the Farside Highlands, the ancient crust is covered by a broken outer layer that records the steady work of impact. This layer is called regolith, a term for loose material resting above solid bedrock. On the Moon, regolith consists of dust, sand-sized grains, small rock fragments, glassy particles, and larger broken pieces thrown out by impacts and then altered by later collisions. It is not soil in the earthly sense, because it contains no living matter, no water-driven chemistry, and no roots or microbes. It is instead a ground of shattered mineral debris, produced by endless mechanical change under airless conditions. This surface layer forms because the Moon has no atmosphere to stop incoming meteoroids. Even very small particles strike at high speed. Each impact breaks rock, melts part of it, and throws debris outward. Larger impacts excavate deep material and spread it over wide areas. Smaller impacts continue to strike the ejector from older collisions, breaking it down again. Over immense spans of time, this repeated process turns exposed rock into a blanket of loose fragments. The regolith therefore acts as both residue and archive. It is the product of bombardment, and it also stores the traces of the bombardment within its grains. On the far side, regolith thickness varies from place to place. In old highland regions, it can be several meters deep and sometimes more, especially where the surface has remained exposed for very long periods, in younger crater floors or on steep slopes. It may be thinner where fresh material is exposed or loose debris has moved downslope. Measurements from orbit, impact experiments, and the study of lunar samples suggest that the upper layer is complex rather than uniform. Fine dust may dominate the topmost part, while coarser fragments lie below in mixed and uneven layers. The texture of this material is unlike ordinary terrestrial sediment. On Earth, water rounds grains as they tumble and dissolve. Wind also smooths and sorts particles. On the Moon, the absence of liquid water and moving air means grains remain angular. Many are sharp-edged, jagged, and irregular. Some particles consist of crushed mineral fragments. Others are tiny beads of glass formed when impacts briefly melt, rock, and fling droplets outward, where they cool rapidly. Still others become welded together into agglutinates, clumps created when micrometeoroid impacts melt fine particles and fuse them with fragments of mineral and glass. These agglutinates are common in mature lunar regolith and help define its unusual physical behavior. The word mature, in this context, describes regolith that has been exposed and reworked for a long time. Mature regolith tends to contain more tiny impact glass, more agglutinates, and more signs of what is called space weathering. Space weathering is the gradual alteration of exposed grains by micrometeoroid impacts and the solar wind. Tiny impacts melt and vaporize small amounts of material. Charged particles from the sun implant themselves into grain surfaces and modify their chemistry. Over time, these processes darken and redden the optical properties of the surface, meaning that the reflected light changes in predictable ways. On the bright far side highlands, this weathering still occurs, though the underlying composition remains lighter than the basalt-rich maria of the near side. The uppermost regolith responds strongly to light. Sunlit dust appears bright, while shadowed hollows become very dark, because the grains are fine and loosely packed near the surface. Footprints, rover tracks, or the disturbance from landing exhaust can alter its texture immediately. Apollo observations on the near side show that lunar regolith can compress under pressure, holding sharp impressions. The same physical principles apply on the far side. Fine grains shift, compact, and cling in small amounts to surfaces, especially when disturbed. Dust behavior on the Moon is influenced by electrostatic charging as well as by mechanical motion. Sunlight can cause the surface to emit electrons, while shadowed regions can accumulate different charges through interaction with plasma in space. These differences may allow very fine dust grains to lift slightly or move under certain conditions, especially near the boundary between day and night. Observations suggest that electrostatic effects are real. Though the scale and frequency of visible dust transport remain uncertain, what is clear is that fine lunar dust is persistent, abrasive, and difficult to manage once it adheres to equipment. Below the finest layer, the regolith contains fragments from many sources mixed together. A single scoop of lunar regolith may include material from local bedrock, ejecta from distant craters, droplets of impact melt, and grains altered by exposure over different lengths of time. This mixing process is called gardening. The term refers to the continual overturning and stirring of the upper ground by impacts. Gardening does not occur evenly or quickly by human standards, but over millions and billions of years it profoundly rearranges the surface. Older grains are buried, newer grains are exposed, and materials from different depths and distances become blended. This mixing makes regolith scientifically valuable. It preserves a record of both local geology and regional impact history. Tiny fragments may come from bedrock no longer exposed nearby. Glass particles may preserve the chemistry of individual impact events. Implanted solar wind particles can reveal aspects of solar history. In some cases, regolith may even contain fragments blasted from other locations on the Moon by large collisions. The surface layer is therefore not merely debris, it is a dispersed collection of samples assembled by natural impact processes. Mechanically, the regolith behaves as a loose granular material under low gravity. The Moon's gravity is much weaker than Earth's, so grains settle and slide differently. Slopes can remain stable at angles that still allow gradual movement of loose material. Disturbance sends particles into ballistic arcs, meaning they travel like thrown objects under gravity, without air resistance. Larger fragments may bounce and roll for considerable distances after an impact or a mechanical disturbance. Finer grains can hang briefly in motion before settling, but they do not drift as dust does in air. The colour and reflectivity of far-side regolith reflect the dominance of highland material. It is generally brighter than the dark volcanic soils developed over basalt plains. Highland regolith tends to be rich in feldspar-derived fragments and poorer in iron and titanium than many Maria deposits. This compositional difference influences both appearance and temperature response. Brighter material reflects more sunlight, though local texture and angle still matter greatly. Fresh crater ejecta often appears especially bright because it exposes less weathered material from below the surface. When a fresh impact occurs, it excavates through the regolith and into more coherent rock beneath. The result is a temporary window into less altered material. Over time, new impacts begin to break down that exposed rock, and the cycle resumes. In this way, the regolith is constantly renewed at the smallest scales while remaining ancient in its overall existence. It is not a fixed blanket laid down once. It is an active outer skin, slowly churned by impacts and altered by radiation. Across the far side, this impacted surface layer lies everywhere between open space and solid crust. It receives the first force of incoming particles, holds the imprint of old collisions, and mediates every contact between machine and ground. Dust, shards, glass, and broken stone together form the immediate reality of the lunar surface. The far-side highlands may appear from orbit as ancient rock, but at close range that rock is concealed beneath a deep, restless layer of debris, made grain by grain through the long and silent work of impact. Across the far side, the loose surface layer rests upon a landscape dominated by impact structures. Craters and basins define this region more completely than any other visible process. They vary from pits too small to notice from orbit to enormous depressions stretching across hundreds or even thousands of kilometers. Together they form a record of collision that reaches back to the earliest history of the Moon. This record is not orderly in the sense of a written archive. It is fragmented, overwritten, and mixed by later events. Even so, the shapes of craters and basins preserve a broad sequence of bombardment that remains central to lunar science. A crater begins when an incoming body strikes the surface at very high speed. The process is not like a slow pressing or a simple blow. At typical impact speeds in the solar system, the energy released is enormous. Rock behaves for a brief moment almost like a compressed fluid under extreme shock. The projectile and the target both deform, melt, and partly vaporize. A shock wave moves outward through the ground, excavating a cavity and hurling material away from the impact point. This initial cavity does not remain unchanged. Its walls may collapse inward, the floor may rebound, and the final crater takes shape within minutes. Small craters tend to be simple in form. They are bowl-shaped depressions with raised rims and surrounding ejecta. Their walls slope inward smoothly, and they usually lack complex internal structures. Larger craters behave differently because the energy involved is much greater. Their walls become unstable and slump downward in terraces. Their floors rebound upward after the compression of impact, sometimes forming central peaks. These peaks are not volcanic cones. They are uplifted crust. Pushed upward by the rapid release of pressure after the impact shock passes, in very large craters, the central uplift can become more complex, forming peak rings or irregular interior mountains. The far side contains craters in extraordinary abundance. From orbit, almost every part of the terrain shows overlapping rims and circular depressions. Many older craters are partly erased by newer ones. Some remain visible only as arcs of broken wall or as slight circular patterns in topography and composition. Others stay remarkably crisp, with sharp rims, blocky ejecta, and bright rays of fresh material. The difference reflects relative age. Younger craters usually preserve clearer forms because they have had less time to be altered by later impacts and the steady breakdown of exposed rock. Crater rays are streaks of ejected material spread outward from a fresh impact. On the Moon, they can extend for hundreds of kilometers. They appear brighter than their surroundings when the excavated material is less weathered than the older surface. These rays slowly fade over time as space weathering darkens them and later impacts mix them back into the surrounding regolith. Their presence, therefore, helps identify relatively young events. On the far side, ray systems cross older terrain and reveal how one impact can spread material widely across an already cratered surface. The distribution of crater sizes also matters. A surface marked only by large craters would tell one kind of story, while a surface crowded with both large and small craters tells another. On the far side, the full spectrum appears. Large impact structures establish the broad architecture of the terrain, while countless smaller craters modify nearly every slope and plane. This pattern reflects both the ancient period of intense bombardment in the early solar system and the continued accumulation of smaller impacts afterward. Observations indicate that the oldest lunar surfaces preserve evidence of the late heavy bombardment hypothesis in broad form. Though the exact timing and intensity of that early spike remain subjects of active study, what is well supported is that the Moon records a period of much heavier impact activity early in its history, followed by a long decline. Basins are the largest members of this impact family. They form when collisions are powerful enough to excavate huge volumes of crust and leave structures far larger than ordinary craters. A basin often includes one or more rings, broad depressed interiors, and uplifted or fractured zones around its margins. Later impacts can obscure these forms, making them difficult to trace without detailed topographic and gravity data. On the far side, many basins remain recognizable because they were not buried as extensively by dark volcanic lava as similar structures on the near side. Their outlines, though worn, still shape regional elevations and crustal patterns. When scientists identify and compare craters, they look at several features. Rim sharpness gives a clue to freshness. Ejecta texture shows how recently material was emplaced. The number of smaller craters superposed on a larger one helps establish relative age. A crater covered by many later impacts is older than one that lies across them with fewer overprints. This method, called crater counting, does not produce a perfect calendar on its own. But when calibrated with sample ages and other measurements, it becomes one of the main tools for dating lunar surfaces. The far side, with its dense preservation of impact terrain, provides a particularly important field for this work. The repeated formation of craters also changes the physical state of the crust near the surface. Impacts fracture rock, weaken slopes, and generate thick deposits of ejecta and melt. Impact melt forms when the heat of collision melts target rock. This melt can collect in pools, sheets, or ponds within and around craters, then cool into solid rock. Some crater floors contain such frozen melt deposits, later broken by further impacts. In larger events, melt production can be extensive and can contribute significantly to local geology. The far side's crater population also reveals a symmetry in appearance between the two hemispheres. The near side has many large basins as well, but broad dark maria fill a number of them and soften their visual dominance. On the far side, the impact forms remain more exposed. The result is not that the far side necessarily received all impacts while the near side remained sheltered. Rather, both hemispheres record heavy bombardment. But later volcanic flooding changed the near side more extensively. On the far side, the original architecture of collision remains more visible at the surface. Some craters contain permanently shadowed regions near the poles, where sunlight never reaches certain interior slopes. Others host boulder fields, mass-wasting deposits, and small landslides caused by the long-term settling of broken material. These details show that even in an airless world, crater interiors continue to evolve. Gravity pulls debris downslope. Small impacts shake loose material and disturb unstable blocks. Thermal cycling. The repeated expansion and contraction caused by large swings in temperature may also help weaken exposed rock over time. These changes are slow, but across great ages they modify the forms left by the original collision. There is no single far-side crater that stands apart from this wider pattern as an isolated marvel. Instead, the scientific force of the region lies in the sheer density and preservation of impact structures across many scales. The land is a surface of excavation, collapse, uplift, and burial repeated again and again. Every crater marks an event in which rock was shattered, displaced, and reassembled. Every basin records a collision large enough to reshape whole provinces of crust. Together they make the far side less a smooth globe than a visible history of bombardment written directly into stone. The surface layer of dust and broken fragments conceals some details, but the circular forms remain unmistakable. They are the dominant structures of this region, and they hold the moon's clearest record of repeated impact from the depths of time. Within the already cratered terrain of the far side lies a structure of far greater scale than the surrounding features. It extends across a vast portion of the southern hemisphere and reaches toward the pole. This structure is known as the South Pole Aitken Basin. It is one of the largest confirmed impact basins in the solar system. Its diameter is roughly 2,500 kilometers, and its depth relative to surrounding highlands is several kilometers from orbit. Its presence is not always obvious as a single clean circle, because later impacts and geological processes have altered its form. Yet through careful mapping of elevation, gravity, and composition, its outline becomes clear as a broad, ancient depression. The basin's size means that it does not appear as a simple crater. Instead, it forms a region where the crust has been deeply excavated and modified. The impact that created it occurred very early in lunar history, likely more than 4 billion years ago, during a time when large collisions were more common. At that time, the moon's crust was still relatively young and possibly thinner in places. When the impacting body struck, it released energy on a scale far beyond that of ordinary craters. Rock was not only shattered and displaced, but also melted in large volumes and thrown outward across immense distances. The initial formation of the basin followed the same general stages as smaller impacts, but on a much larger scale. A transient cavity opened under the force of the collision. Shock waves travelled through the crust and into the deeper interior. Material near the impact point was compressed, heated, and accelerated outward. As the cavity expanded, its walls became unstable and began to collapse inward. The floor rebounded under the release of pressure, lifting deep material upward. The final structure included multiple rings, broad depressions, and uplifted regions. Over time, these features became less distinct due to later impacts and gradual modification, but their large-scale pattern remains detectable. One of the most significant aspects of the South Pole Aitken Basin is the depth of excavation. In many places on the Moon, impacts penetrate only the upper crust. In this basin, the energy of the collision likely reached deeper layers. possibly exposing material from the lower crust or even from the upper mantle. The mantle is the layer beneath the crust, composed of different mineral assemblages and formed under different conditions. Observations from orbit, especially through spectral analysis and gravity mapping, suggest that some materials within the basin differ from typical highland composition. These differences indicate that deeper layers may have been brought closer to the surface. The surface within the basin shows variation in both composition and texture. Some regions contain smoother plains compared to the surrounding highlands, while others remain heavily cratered. The smoother areas are not as extensive or as dark as the large basalt plains on the near side, but they may include deposits of impact melt or limited volcanic flows that occurred after the basin formed. The presence of these materials suggests that the basin influenced later geological processes by altering the local structure of the crust and the distribution of heat. Gravity data provides further insight into the basin's structure. Measurements from orbit reveal anomalies, meaning variations in gravitational strength that correspond to differences in density below the surface. In the case of the South Pole Aitken Basin, these anomalies indicate that the crust is thinner within the basin than in surrounding regions. This supports the idea that the impact removed or displaced a large volume of crustal material. It also suggests that denser material from deeper layers lies closer to the surface here than elsewhere on the far side. The basin's formation had long-term consequences for the Moon's evolution. By removing and redistributing crustal material, it may have affected how heat moved within the Moon's interior. Regions of thinner crust can allow heat to escape more easily, while thicker crust acts as an insulating layer. The far side as a whole is thought to have thicker crust than the near side, yet within this basin the thickness is reduced. This contrast creates a complex pattern in which one of the deepest structures on the far side interrupts the general trend of thick highland crust. Later impacts have modified the basin extensively. Large craters formed within it, overlapping its original structure and obscuring some of its boundaries. Smaller impacts continue to reshape its surface, adding layers of regolith and breaking down exposed rock. Despite this ongoing modification, the basin remains identifiable because of its overall size and the consistent pattern of lower elevation and distinct composition compared to surrounding terrain. The location of the basin near the lunar South Pole adds another dimension to its character. Parts of its interior lie at high latitudes where the sun remains low on the horizon even during daylight periods. This creates long shadows and regions that receive very little direct sunlight. Some areas may remain in permanent shadow, particularly within deep craters along the basin's edges. These conditions influence temperature and the potential for volatile materials. Though the detailed behavior of such materials depends on local topography and exposure, scientific interest in the South Pole Aitken Basin is strong because it offers a window into early lunar history. By studying materials exposed within it, researchers hope to better understand the composition of deeper lunar layers and the processes that shape the Moon shortly after its formation. Samples from this region, if returned to Earth, could provide direct evidence of the Moon's internal structure and the nature of large impact events in the early solar system. Observations indicate that the basin is not uniform in its internal structure. Variations in composition and elevation suggest that different parts of the basin experience different conditions during and after the impact. Some regions may have been filled with melt, while others retained fractured blocks of original crust. Over billions of years, these differences have been partly masked by new impacts and the steady accumulation of regolith, yet they remain detectable through careful analysis. The South Pole Aitken Basin stands as a central feature of the far side not because it dominates the surface visually in every view, but because it represents a profound event in lunar history. It is a region where the outer layers of the Moon were deeply disturbed, where material from below was brought closer to the surface, and where later processes unfolded on a foundation altered by a single immense collision. Within the broader pattern of craters and highlands, it forms a distinct province, defined by scale, depth, and the lasting imprint of one of the most powerful impacts recorded on any planetary body. Across the far side highlands and within the broad expanse of the South Pole Aitken Basin, the surface materials reveal a complex mixture of rocks that reflect both early formation and later alteration. These rocks do not lie exposed in clean, continuous layers. Instead, they are fragmented, mixed, and redistributed by countless impacts. Even so, their composition can be studied through orbital measurements, laboratory analysis of lunar samples linked to similar terrains, and comparisons across different regions of the Moon. Together, these approaches provide a consistent picture of the far side surface as a place dominated by ancient crustal material, with localized additions from impact melt and limited volcanic activity. The most common rock type associated with the Farside Highlands is anorthosite. This rock is light in colour and rich in feldspar minerals, especially calcium-rich plagioclase. Feldspar forms when molten material cools and crystallizes under specific conditions. In the early history of the Moon, a large portion of its outer layer is thought to have been molten, forming what is called a magma ocean. As this molten layer cooled, denser minerals sank while lighter minerals floated upward. The floating minerals solidified into a buoyant crust composed largely of anorthosite. The far side preserves much of this original crust, though it has been broken and altered by later events. Anorthosite on the Moon differs from similar rocks on Earth in several ways. It lacks the influence of water and atmospheric chemistry. Its crystals formed in a dry environment and remained exposed to vacuum and radiation for billions of years. Over time, impacts shattered the original rock into fragments that now exist within the regolith. Some larger blocks remain intact within crater walls and central peaks, where deeper material has been lifted to the surface. These exposures allow scientists to infer the composition of the crust beneath the loose surface layer. In addition to anorthosite, the far side contains basalt in smaller quantities. Basalt is a darker, denser rock that forms from cooled lava. On the near side of the Moon, large areas of basalt fill impact basins, creating the dark maria visible from Earth. On the far side, basaltic deposits are less extensive. They appear mainly as smaller patches within certain basins or low-lying areas. These deposits indicate that volcanic activity did occur on the far side, but it was more limited. The reasons for this difference relate to internal heat and crustal thickness, which influence how easily molten material can reach the surface. The basalt found on the far side shares many characteristics with that on the near side, including its composition of minerals such as pyroxene and olivine, which are rich in iron and magnesium. However, variations exist in the relative amounts of these minerals and in trace elements. These variations provide clues about the conditions under which the lava formed and the source regions within the Moon's interior. Spectral data from orbiters detect differences in how these rocks reflect sunlight at different wavelengths, allowing scientists to map their distribution across the surface. Impact processes contribute additional rock types and materials. When an impact is large enough, it can melt significant volumes of rock. This molten material can pool and then cool into solid rock known as impact melt. Such rocks often have a different texture from both anorthosite and basalt. They may appear smoother and more uniform at certain scales, though later impacts can break them apart and mix them into the surrounding regolith. In some cases, Impact melt can form glassy coatings or droplets that become part of the surface layer. Within the South Pole Aitken Basin and other large structures, there is evidence of materials that differ from typical highland composition. These materials may originate from deeper layers of the Moon, brought closer to the surface by the energy of large impacts. Observations indicate variations in mineral content that suggest a mixture of lower crust and possibly upper mantle components. The mantle is composed of minerals that formed under higher pressure and temperature conditions than those in the crust. Detecting these materials at or near the surface provides rare insight into the Moon's internal structure. The distribution of elements also varies across the far side. Some regions show lower concentrations of elements that produce heat through radioactive decay, such as uranium and thorium, compared to the near side. These elements influence the thermal evolution of the Moon because their decay releases energy over long periods. Their uneven distribution affects where volcanic activity is more likely to occur. On the far side, the relative scarcity of these elements contributes to reduced volcanic resurfacing, allowing the older crust to remain exposed. Rocks on the far side also carry the effects of space weathering. As with the regolith, exposed rock surfaces are altered by micrometeoroid impacts and solar wind particles. These processes create thin coatings on grains, embed tiny particles of metallic iron, and change the way light reflects from the surface. Over time, even brighter northocite can become slightly darker and more subdued in color. Fresh exposures created by recent impacts appear brighter because they reveal less altered material beneath the weathered surface. Large boulders scattered across crater floors and slopes provide visible examples of intact rock. These boulders often originate from deeper layers exposed during impacts. Their size and shape depend on the energy of the event that produced them and the subsequent movement of material downslope. Without atmospheric erosion, these rocks can persist for long periods, gradually breaking down through thermal stress and further impacts. Their presence offers opportunities to study the properties of lunar rock at scales larger than individual grains. The chemical composition of far-side rocks is measured through a combination of remote sensing and laboratory analysis. Orbiting instruments detect characteristic signatures in reflected light or emitted radiation that correspond to specific elements and minerals. These measurements are calibrated using samples returned from the Moon, though most samples come from near-side locations. By comparing spectral signatures, scientists can extend their understanding to far-side regions. While this method is well established, it carries some uncertainty because direct sampling of far-side material is limited. Observations indicate strong consistency with models of lunar crust formation, but finer details remain an area of ongoing study. The mixture of rock types across the far side reflects a long sequence of processes. Initial crust formation produced a feldspar-rich surface. Large impacts excavated and redistributed this material, while also introducing melt and exposing deeper layers. Limited volcanic activity added basalt in certain areas. Continuous bombardment then fragmented and mixed all these components into the regolith. Each grain and fragment carries part of this history. Together, they form a surface that is not uniform but instead composed of many overlapping contributions from different times and depths. The far side's rocks do not present a single dramatic discovery. They reveal something more gradual and persistent. They show that the Moon's outer layers formed early, that impacts reshaped them repeatedly, and that internal processes varied across the globe. The composition of these rocks aligns with a broader understanding of lunar evolution, grounded in observation and measurement. What emerges is a surface built from ancient crust, modified by impact, and only lightly altered by later volcanism. The materials themselves remain quiet, but within them lies a detailed record of formation, disruption, and slow change over billions of years. Beneath the broken rocks and dust of the far side lies the crust itself, a thick outer shell of solid lunar material that preserves some of the oldest large-scale structure of the Moon. This crust is not visible as a clean layer from the surface because impacts have fractured, excavated, and mixed its upper parts over immense spans of time. Yet its broader form can be measured through gravity mapping, topography, seismic inference, and the study of exposed materials in crater walls and central peaks. These observations indicate that the far side crust is, on average, thicker than the crust on the near side. That difference is one of the most important global asymmetries of the Moon. Crust, in this setting, means the outermost solid layer of the Moon, lying above the deeper mantle. It forms early in lunar history as the outer portion of the Moon cools and crystallizes. In the standard model of lunar formation, a large impact in the early solar system produces debris that eventually gathers into the Moon. The young Moon then holds enough heat to maintain a deep molten outer layer, often described as a magma ocean. As this molten material cools, denser minerals sink while lighter, feldspar-rich minerals rise and solidify near the top. This process creates a primary crust rich in anorthositic rock. The far side preserves a large part of this ancient shell. The thickness of the crust is not uniform across the Moon. Measurements from missions that map the gravitational field, especially through precise tracking of orbiting spacecraft, show that the near side generally has thinner crust beneath many of its broad volcanic plains, while the far side tends to retain thicker, more elevated crust. In some regions, this difference amounts to many kilometers. Exact values depend on the model and method used, but the broad pattern is robust. Observations consistently show a thicker far side crust and a thinner near side crust on average. This asymmetry helps explain several visible differences between the hemispheres. A thinner crust is easier for rising magma to penetrate, especially if internal heat remains available. A thicker crust acts as a stronger barrier. On the near side, large basins were more often flooded by basaltic lava, producing the dark Maria seen from Earth. On the far side, similar flooding was far less extensive. The crust there appears to have remained more resistant to volcanic resurfacing, allowing ancient highland terrain to stay exposed. The surface pattern therefore reflects the deeper structure below it. The crust also influences the topography of the far side. Because it is thicker and composed largely of ancient highland material, broad regions stand at higher average elevation than many near-side Maria. This does not mean the far side is uniformly raised in a simple way. Large impact basins interrupt the pattern, and local relief remains complex. Still, when viewed globally, the far side appears more elevated and more dominated by primary crustal terrain. The landform matches the internal architecture. How this crustal asymmetry develops remains an area of active study. Several explanations have been proposed, and some may work together. One idea is that the near side remains warmer for longer during early lunar history, perhaps because heat-producing elements become concentrated there. This prolonged warmth could inhibit crustal thickening or encourage later melting and volcanism. Another possibility involves the thermal effects of Earth shortly after the Moon forms, in early models. The side of the young Moon facing the still hot Earth may cool differently from the far side, contributing to uneven crust formation. Observations indicate that asymmetry is real and long-lived, but the full combination of causes remains uncertain. The crust is not a simple, unbroken shell of uniform material. It contains fractures, buried impact structures, local variations in composition, and regions where large impacts have excavated deeply enough to expose lower levels. Basin-forming collisions disrupt the crust on enormous scales. They thin it locally, uplift deeper material, and redistribute debris across wide distances. The South Pole Aitken Basin provides a strong example. Within that basin, the crust is thinner than in surrounding Farside highlands, showing that even the thicker Farside shell can be profoundly altered by extreme impact. The crust therefore retains both its primary structure and the scars of later events. Gravity measurements are especially useful in revealing buried crustal patterns. When a spacecraft passes over a region of slightly denser or less dense material, its motion changes very subtly. By tracking these changes with great precision, scientists can infer variations in mass distribution below the surface. On the Moon, this approach has revealed crustal thickness patterns and structures hidden beneath visible terrain. Some impact basins contain mass concentrations, often called mascons, formed by dense material associated with basin formation and later filling. These affect spacecraft orbits and help illuminate how crust and mantle respond to giant impacts. The Farside crust also acts as a long-term recorder of the early solar system. Because it undergoes less volcanic resurfacing than much of the near side, large portions of it preserve ancient surfaces and structures. Every impact does alter the crust, but many of those impacts date from very early times. The crust is therefore both damaged and preserved. It is damaged in the sense that collisions fracture and excavate it. It is preserved in the sense that later molten flows do not bury it on the same scale as on the near side. This makes the far side especially valuable for reconstructing early lunar history. The composition of the crust reflects its origins. It remains rich in feldspar-dominated and orthositic material, especially in the upper crust. Deeper levels may include more diverse rocks, including mafic materials richer in iron and magnesium. Large impacts expose some of these deeper layers, but the general picture remains one of a thick, buoyant highland crust. Its mineral content, density, and thickness all support the view that it forms from early differentiation, meaning the separation of material by density and chemistry as the Moon cools and solidifies. The crust also mediates the transfer of heat from the interior to the surface. Thick crust tends to insulate, slowing the escape of heat from below. This does not stop heat flow, but it affects how long subsurface regions remain warm, and whether melting can occur at depths capable of feeding eruptions. On the far side, the combination of thicker crust and lower concentrations of certain heat-producing elements appears to reduce the likelihood of extensive volcanic flooding. The result is a surface where the primary crust remains more visible and the geological record stays closer to its early form. Seen in this way, the Farside crust is not merely a hidden shell beneath the regolith. It is the structural foundation of the hemisphere's character. It determines broad elevation, influences volcanic history, preserves ancient highland rock, and stores the effects of the greatest impacts. It is thicker, older in appearance, and less resurfaced than much of the near side. Beneath the dust and cratered uplands, this buried framework holds the Moon's deep asymmetry and solid form. The far side looks different because, at depth as well as at the surface, it is built differently. Below the thick Farside crust, the Moon's earlier warmth leaves traces in rock chemistry, volcanic patterns, and the uneven distribution of certain elements. These traces do not appear as glowing regions or active chambers of magma in the present Moon. The far side today is largely cold and geologically quiet at the surface, yet its ancient interior once contains enough heat to melt rock, drive magmatic movement, and shape the contrast between the two hemispheres. To understand why the far side has fewer broad volcanic plains than the near side, it is necessary to look inward to the history of heat, melt, and the elements that slowly release energy through radioactive decay. In planetary science, magma is molten rock below the surface. Lava is the same material after it reaches the surface and cools in the open. The Moon once has abundant molten material during its earlier stages, first as a deep outer magma ocean and later as more localized zones of internal melting. As the Moon cools, this molten state does not disappear all at once. Heat remains trapped inside, especially where insulating crust, internal composition, and the decay of radioactive elements allow temperatures to stay elevated. Over time, pockets or regions of partial melt can still form, rise, and in some places break through to the surface. The near side of the Moon shows extensive evidence of this later volcanic history. Large impact basins there become flooded by basaltic lava, creating the Maria visible from Earth as dark plains. On the far side, these broad flood basalts are much less common. This difference is not because the far side entirely lacks heat or magma. Smaller basaltic deposits do exist there, and volcanic activity clearly occurs in limited regions. The difference lies in scale and frequency. The far side experiences far less widespread lava flooding, and the reason appears to involve both crustal thickness and the internal distribution of heat-producing elements. Certain elements release heat as their unstable atomic nuclei slowly decay over immense spans of time. Among the most important on the Moon are uranium, thorium, and potassium. These are called heat-producing or radioactive elements in geological discussion. Their decay does not create intense heat quickly, but across millions and billions of years it contributes significantly to the thermal evolution of a planetary body. Where these elements are more concentrated, rock can remain warmer for longer. This warmth can help sustain melting in deeper layers or delay cooling in the crust and upper mantle. Orbital measurements indicate that these heat-producing elements are not spread evenly across the Moon. They are more concentrated in a region associated mainly with the near side, especially around the Procellarum area and parts of the near-side volcanic provinces. This geochemical province is often linked to what scientists call creep, a term derived from potassium, rare earth elements, and phosphorus. Creep does not refer to a single rock type in the ordinary sense. It refers to material enriched in these incompatible elements, meaning elements that tend not to fit easily into the crystal structures of major minerals during cooling, and therefore become concentrated in the remaining melt. As the lunar magma ocean crystallizes, these incompatible elements gather into the last portions of liquid and later become concentrated in specific regions. The far side appears to contain much less of this enriched material. That difference matters. If the near side retains a greater concentration of heat-producing elements, then it stays warmer for longer and is more capable of sustaining the melting that feeds large-scale basalt volcanism. The far side, with fewer such elements and thicker crust above, becomes less favourable for extensive lava eruption. Observations support this overall pattern, though the precise sequence by which the enrichment becomes concentrated remains uncertain. Some models suggest that internal overturn, asymmetrical cooling, or large impacts help redistribute this material early in lunar history. Heat alone does not guarantee volcanism. Molten material must also be able to rise through the crust. The far side's thicker crust makes this ascent more difficult. Magma generated at depth must push upward through a longer, stronger barrier. Some of it may cool and solidify before reaching the surface. Some may stall at depth entirely. On the near side, thinner crust allows magma to reach basin floors more easily, especially where giant impacts have already weakened the crustal structure. The surface expression of this difference is clear in the patchy and limited far-side volcanic deposits compared with the vast near-side Maria. The mantle below the crust likely plays a direct role in this history. The mantle is composed of denser silicate rocks rich in iron and magnesium. As the moon cools, portions of the mantle may partially melt under the right conditions of temperature and pressure. These melts are thought to be the source of the basaltic lavas that later erupt onto the surface. If the mantle beneath the near side remains hotter for longer, then melt generation there becomes more sustained. If the far side cools more effectively or receives less radiogenic heating, then mantle melting there becomes less extensive. The difference need not be extreme in every location. Even modest variations, maintained over long spans of time, can create very different surface outcomes. Large impacts may also influence this internal heat history. A basin-forming collision thins the crust locally, fractures it deeply, and can alter the movement of heat and melt afterward. On the near side, some giant basins later fill with enormous volumes of lava. On the far side, even where basins form, the later flooding is often smaller. This suggests that impact alone is not enough. It must combine with favourable thermal and structural conditions. Where those conditions are absent or weaker, the basin remains largely a scar of impact rather than a container for widespread lava seas. The fading of heat is a slow process. The moon is small compared with Earth, and smaller bodies lose internal heat more quickly. Over time, the energy available for large-scale melting decreases. Volcanic activity declines, crust and mantle cool further, and the surface becomes increasingly dominated by impact rather than internal renewal. By the present era, the moon no longer shows active volcanism in the accepted scientific sense. There have been discussions of geologically recent volcanic features in some locations, and certain small irregular mare patches may indicate volcanism that continues later than once thought. Even so, this activity remains ancient on human timescales and limited compared with the major volcanic epochs of the moon's past. The far side, therefore, preserves a quieter outcome of lunar cooling. Its thick crust and lower abundance of heat-producing elements mean that much of its surface escapes burial beneath later basalt. The ancient highlands remain exposed. The scars of impact stay visible. The original crustal character survives more clearly. This is not because the far side is untouched by internal processes, but because those processes operate with less force at the surface and over a more restricted area. In this deeper region of explanation, the far side becomes a place where absence carries meaning. The missing expanses of dark lava are evidence of thicker crust. The reduced volcanic flooding reflects uneven internal heat. The scarcity of enriched radioactive elements helps explain why one hemisphere stays geologically more subdued. Beneath the broken surface and the buried crust lies the story of a moon that cools unevenly, with warmth lingering longer on one side than the other. On the far side, that warmth fades more completely, leaving behind a hemisphere where ancient crust remains exposed under the long and quiet decline of internal fire. Beneath the crust and below the long-faded pathways of rising magma, the deeper interior of the moon can only be known indirectly. No drill reaches such depths. No human or robotic mission has opened the mantle or touched the core. Knowledge of these regions comes instead from signals that pass through the moon, from measurements of gravity and rotation, and from physical models tested against those observations. The picture that emerges is incomplete in detail, but strong in outline. The far side does not reveal a separate hidden world beneath its surface. It reveals the same moon at depth, though the clues available there help constrain how that interior is built and how it changes over time. One of the most important tools for probing deep structure is seismology, the study of vibrations that move through a planetary body. A seismic wave is a pulse of energy that travels through rock after an event such as an impact or a moonquake. Moonquakes are natural tremors within the moon. Some are deep, occurring hundreds of kilometers below the surface. Others are shallow, though usually weaker than many earthquakes on Earth. Additional signals come from thermal cracking, meteoroid impacts, and the deliberate crashing of spacecraft stages during earlier missions. Instruments placed on the moon during the Apollo era record many such vibrations and show that the moon is not entirely silent inside. These seismic records do not come from the far side directly, because the Apollo seismometers are set on the near side. Even so, waves pass through large portions of the moon and allow global inferences. Their behavior indicates that the moon is internally layered. The crust forms the outer shell. Below it lies the mantle, a much thicker region composed mainly of solid silicate rock. Deeper still lies a small core, rich in metallic iron and likely containing some sulfur and perhaps other lighter elements. The exact size and state of the core are constrained by several lines of evidence, though uncertainty remains in the details. The mantle occupies most of the moon's volume. It is not molten in the ordinary present-day sense. It is mainly solid rock that can deform very slowly over long spans of time. In earlier lunar history, parts of it partially melt, producing the basaltic magmas that later erupt at the surface. In the present moon, observations indicate that the mantle is largely cool and rigid compared with Earth's mantle, though not entirely uniform. Some regions may remain warmer than others, and a small partially molten layer has been proposed near the base of the mantle, or at the top of the core based on seismic and rotational data. Observations support the existence of deep internal complexity, but the exact extent of any remaining melt remains uncertain. Seismic waves help distinguish these layers because different materials transmit them differently. Some waves compress and expand rock along their direction of travel. Others shear the material sideways. Their speeds depend on density, rigidity, temperature, and composition. When they encounter a boundary between layers, they may reflect, refract, or weaken. By measuring arrival times and patterns, scientists infer the depth and nature of internal transitions. On the moon, this method suggests a mantle extending downward for more than 1,000 kilometers beneath the crust before giving way to the core region. The core itself appears small relative to the moon's total size. Multiple studies using seismic information, laser ranging, and the moon's response to gravitational forces indicate a metallic core with an outer liquid portion and likely a solid inner part. The liquid outer core is important because moving conductive fluid can support a magnetic dynamo under suitable conditions, though that process belongs to the moon's earlier history more than to its present state. The core's radius is only a fraction of the lunar radius, much smaller in proportion than Earth's core. This fits the moon's lower density and its origin from material poor in metallic iron compared with the planet's. Gravity mapping strengthens this internal picture. Orbiting spacecraft experience tiny changes in motion when they pass over regions of differing mass distribution. By tracking these changes precisely, scientists reconstruct the moon's gravity field, combined with topography. This field reveals how the crust and mantle support surface loads such as mountains, basins, and volcanic fills. Some regions are close to isostatic balance, meaning that topographic highs and lows are partly compensated by density differences at depth. Others retain signatures of buried impact structures or dense intrusions. On the far side, gravity data has been especially important because it allows scientists to infer hidden structure even where direct surface sampling is absent. The South Pole Aitken Basin again becomes central at this depth. Because the basin is so large, its formation likely perturbs not only the crust but also the upper mantle. Gravity and compositional data suggest that denser material lies closer to the surface within it than in surrounding farside highlands. This supports the view that the giant impact excavates deeply and modifies the underlying structure on a regional scale. The basin therefore acts as a window, not fully open but significantly thinner than much of the farside crust above the mantle. In that sense, the far side provides one of the Moon's best opportunities to study how giant impacts disturb deep interior layers. The Moon's rotation also offers clues. Small variations in how the Moon wobbles and responds to Earth's gravity reveal information about its internal mass distribution and the physical state of its core. Laser ranging experiments, which measure the distance between Earth and reflectors left on the lunar surface, track the Moon's motion with extraordinary precision. These data support the existence of a fluid outer core and help constrain the size of internal layers. The Moon does not behave like a perfectly rigid stone. Its rotation records the presence of internal boundaries and some degree of mechanical decoupling between them. Deep moonquakes add another piece of evidence. These events tend to occur at great depth and are often linked to tidal stresses from Earth's gravitational pull. Their distribution suggests that the deep Moon remains responsive to repeated stress, even though it is largely solid. The pattern of these quakes helps define internal properties and shows that the mantle still transmits and stores stress in an organized way. The Moon's interior is quiet compared with Earth's tectonically active body, but it is not inert in an absolute sense. What emerges from these observations is a layered world beneath the farside crust. The upper mantle consists of ancient silicate rock, largely solid, once hotter and more able to melt. Below it lies a small metallic core, partly liquid, the remnant of deeper differentiation. Between these layers, temperature, pressure, and composition change gradually and sometimes abruptly. The far side does not conceal strange cavities or hidden oceans of molten rock in the modern scientific picture. It conceals something more restrained and more significant, the preserved structure of a small rocky world that cools, differentiates, and carries the fading memory of its earlier heat in the physical properties of its deepest layers. Within the solid rocks of the far side there exist faint traces of magnetism, preserved not as an active field but as a memory of conditions that no longer exist. Magnetism in this context refers to the alignment of tiny magnetic domains within minerals, usually iron-bearing ones, that can lock into place when the material cools in the presence of a magnetic field. This remanent magnetism, meaning magnetism retained after the original field has disappeared, provides clues about the Moon's internal state during earlier periods of its history. The Moon today does not possess a global magnetic field comparable to Earth's. Measurements from orbiting spacecraft show that the lunar magnetic environment is weak and patchy. Instead of a strong cis-just continuous field, there are localized regions where magnetic signatures appear stronger, often associated with particular geological features. These localized fields are embedded in the crust and do not extend outward in a uniform way. The far side contains several such regions, where magnetized rocks create small-scale magnetic anomalies detectable from orbit. These anomalies are not random. Their distribution suggests a link between magnetism and past events such as large impacts and the cooling of molten rock. When an impact melts rock and that melt later cools, any magnetic minerals within it can align with the prevailing magnetic field at that time. Once the rock solidifies, this alignment can become fixed. Similarly, when lava cools at the surface or within shallow layers, It can also record the direction and strength of the magnetic field present during its formation. Over billions of years, these records remain, even after the original field has faded. The presence of remnant magnetism implies that the Moon once had a stronger magnetic field than it does today. This field is thought to have been generated by a dynamo, a process in which the movement of electrically conductive fluid within a planetary core creates a magnetic field. On Earth, this dynamo operates continuously within the liquid outer core. For the Moon, evidence suggests that a similar process may have existed early in its history, though likely weaker and shorter-lived. The Moon's small size and rapid cooling would limit the duration of such activity. Data from lunar samples returned during the Apollo missions show that some rocks carry strong remnant magnetization, indicating that they form in the presence of a magnetic field stronger than the current one. These samples come from the near side, yet their implications extend globally. If the Moon has a dynamo early on, then both hemispheres would experience its effects. The far side's preserved crust, especially within older highland regions and large basins, contains materials that could record this ancient field, though direct sampling there remains limited. One of the notable associations observed on the far side is between magnetic anomalies and impact basins or their ejecta. In some cases, regions surrounding large impacts show enhanced magnetic signatures. One explanation is that the impact process itself contributes to magnetization. The shock of impact can alter minerals and create conditions where magnetic domains align. Alternatively, the heat generated by impact may temporarily reset existing magnetic signatures, allowing them to record the field present during cooling. Observations indicate that both processes may occur, though their relative importance varies with conditions. The South Pole Aitken Basin provides an important context for these studies. Because it is one of the oldest and largest structures on the Moon, materials within and around it may preserve records of early magnetic conditions. Orbital data reveal variations in magnetic strength across the basin, suggesting a complex history of magnetization and subsequent alteration. Some areas show relatively weak magnetism, possibly due to the extreme heating and disruption caused by the original impact, which may erase earlier magnetic signatures. Other regions retain stronger signals, perhaps recording later cooling events in the presence of a magnetic field. The study of lunar magnetism also involves examining how these crustal fields interact with the solar wind. In areas where localized magnetic fields are stronger, they can deflect incoming charged particles slightly, creating miniature magnetospheres on a very small scale. These regions may show differences in surface weathering compared to surrounding areas. For example, some magnetic anomaly regions are associated with high albedo features known as lunar swirls. These swirls appear as bright, sinuous patterns on the surface, and their formation is linked to the interaction between magnetic fields and solar wind particles. The exact mechanism remains under study, but observations indicate that reduced exposure to solar wind can slow the darkening effects of space weathering, leaving these areas relatively brighter. Despite these findings, the overall magnetic environment of the far side remains weak compared to that of Earth. There is no large-scale field to guide compasses or shield the surface from radiation in any significant way. The magnetized regions are small and irregular, and their effects are limited to local scales. The broader significance of lunar magnetism lies not in present conditions, but in what it reveals about the Moon's past. The decline of the lunar magnetic field likely follows the cooling of the core. As the Moon loses heat, the movement of conductive fluid within the core slows. Without sufficient motion, the dynamo process weakens and eventually stops. The timing of this decline is still being refined. Some evidence suggests that the field persists for several 100 million years after the moon forms, while other data indicate that it may last longer in a diminished state. It remains uncertain exactly how long the dynamo operates and how its strength varies over time, but the consensus holds that it is no longer active in the present era. The far side, with its ancient crust and preserved impact structures, serves as a repository for these magnetic records. Each magnetized region reflects a moment when rock cools in the presence of a field, locking in a directional imprint. These imprints are not visible to the eye. They require sensitive instruments to detect and map. Yet they provide a rare form of evidence, one that connects surface geology with deep interior processes that have long since ceased. In this deeper layer of the moon, the sense of hidden discovery comes not from dramatic features but from subtle signals. The rocks of the far side do not emit a strong field or produce observable magnetic effects on a large scale. Instead, they hold quiet traces of a time when the moon's interior is more active, when its core may generate a field, and when cooling rock captures that field in microscopic alignment. These traces persist through billions of years, altered but not erased by later events. They form a record of an internal process that has faded, leaving behind only the residual patterns embedded within the crust. At the far side polar regions, the surface changes in one important way. Light no longer rises high across the sky as it does at lower latitudes. Near the poles, the sun moves close to the horizon throughout the long lunar day, circling at a shallow angle rather than climbing overhead. This geometry creates an environment of long shadows, low illumination, and exceptional cold in places where crater floors and steep depressions never receive direct sunlight. These areas are called permanently shadowed regions. They're among the coldest known places in the solar system, and they provide the main setting in which water ice and other volatile substances may persist on the moon over very long spans of time. A volatile is a substance that can easily change into gas under suitable temperature and pressure conditions. Water is one such substance, so are carbon dioxide, ammonia, methane, sulfur compounds, and several simple organic molecules. On a sunlit lunar surface, many volatiles would not remain stable for long. Heat from direct sunlight would cause them to sublimate, meaning that solid material would pass directly into gas without becoming liquid first. Because the moon has no substantial atmosphere, this gas would then escape, migrate, or become trapped elsewhere. In permanently shadowed regions, however, temperatures can remain so low that some volatiles stay frozen for billions of years. These cold traps form because of the moon's small axial tilt. The moon's rotational axis is tilted only slightly relative to the plane of its orbit around the sun. As a result, the sun never rises far above the horizon at the poles. Deep crater interiors, especially those with steep walls, can therefore remain in permanent darkness. Measurements from orbit indicate that temperatures in some of these regions fall below many tens of degrees above absolute zero. At such temperatures, water ice can remain stable at or near the surface, protected from direct solar heating. The far side includes polar terrain within and around the southern reaches of the South Pole Aitken Basin, where deep craters and complex topography create many candidate cold traps. These areas are difficult to study directly because they are dark, rugged, and often hidden from convenient lines of observation. Even so, a combination of instruments has provided strong evidence that water-related materials exist in some permanently shadowed regions. Neutron spectrometers, radar observations, thermal measurements, and reflected light data all contribute to this picture. One important line of evidence comes from the detection of hydrogen. hydrogen-rich material affects how incoming cosmic rays interact with the lunar surface and how neutrons are emitted back into space. Orbiting instruments measure these neutron patterns and find enhanced hydrogen concentrations near both lunar poles. Hydrogen does not prove the presence of pure water ice by itself. It could also be present in hydroxyl compounds, solar wind products, or mixed volatile deposits. Still, in the coldest shadowed regions, the most widely accepted interpretation is that at least part of this hydrogen is associated with water ice. Additional evidence comes from reflectance and thermal studies. Some instruments detect signatures consistent with surface frost or shallow ice mixed with regolith in a limited number of locations. Radar data has sometimes been used to argue for blocky ice deposits, but radar interpretation is complex. Rough rocky surfaces can produce similar signals under some conditions. For that reason, scientific consensus is cautious. Observations indicate that water ice is likely present in permanently shadowed polar regions, but the exact abundance, purity, depth, and physical form remain uncertain from orbit alone. The source of this ice is also mixed. Some water likely arrives through cometary impacts or water-bearing asteroids that strike the Moon and deliver volatile compounds. Some may form through the interaction of solar wind hydrogen with oxygen in lunar minerals, producing hydroxyl or water at the surface. Micrometeoroid impacts and internal outgassing may also contribute in smaller amounts. Once created or delivered, these molecules can hop across the surface in a process called ballistic migration. Because there is almost no atmosphere, a molecule released by heating can travel in an arc, strike the ground, and either stick briefly, escape, or be released again. Over many such hops, some molecules eventually reach cold traps, where they freeze and accumulate. Not all volatile material at the poles is necessarily ancient and undisturbed. Impacts can excavate, bury, or mix these deposits. Regolith gardening can slowly churn the uppermost layers, even in cold regions. Some ice may lie exposed at the surface in very cold spots, while some may be mixed with dust and rock grains or buried beneath a dry upper layer. There may also be seasonal or cycle-based shifts at very shallow depths, as illumination changes slightly along crater rims and slopes. The general presence of cold-trapped volatiles is supported by observation, but their small-scale distribution remains an active area of study. The far-side polar environment adds an additional scientific advantage, because the Moon shields the far side from much of Earth's radio interference. Polar highlands on that hemisphere combine radio quiet with access to nearby cold traps. This makes the region important not only for volatile science but also for future astronomical and geological investigations. Even so, the terrain is challenging. Low sun angles create sharp lighting contrasts. Permanent darkness complicates imaging and landing. Temperatures in shadowed regions can become severe enough to affect instruments, materials, and power systems. Exploration there requires careful engineering rather than dramatic interpretation. Water ice matters scientifically because it records the movement of volatile compounds through the inner solar system. These deposits may preserve a layered history of delivery from impacts, solar wind chemistry, and surface migration. If sampled directly, they could help clarify how water behaves on airless bodies and how common such cold-trapping processes are elsewhere. The Moon becomes, in this sense, a natural laboratory for volatile preservation under vacuum and extreme cold. There is also practical interest in these deposits. Water can support life support systems and be separated into hydrogen and oxygen for fuel and breathing supplies. This possibility is often discussed in planning for future exploration. Yet the practical value depends entirely on the real concentration accessibility, and physical state of the ice. A region containing only trace ice mixed thinly through dry regolith is very different from one containing richer deposits. At present, orbiting observations strongly suggest presence, but they do not settle the question of usable abundance. In the far side polar cold traps, the Moon shows one of its quietest forms of preservation. Sunlight never reaches some of these floors, heat barely enters. Molecules arriving by chance or by long migration can remain frozen where they settle. Dust accumulates slowly above them or among them. The result is not a hidden sea or a buried cavern of crystal, but a patchwork of frozen traces held in darkness by geometry and cold. In these shadowed hollows, the outermost exposed history of impact and dust gives way to another record, one written in frost, hydrogen, and the long stillness of permanent night. Across the far side of the Moon, direct exploration has come primarily through robotic missions, orbiting spacecraft, and a limited number of surface operations conducted without continuous human presence. These missions do not reveal sudden or unexpected phenomena. Instead, they provide measured data that refines understanding of terrain, composition, and environment. The far side remains scientifically rich, not because it contains unknown forces, but because it preserves conditions that differ from the more frequently observed near side. The first images of the far side arrive from early space missions that pass behind the Moon and transmit photographs after re-establishing communication. These images show a heavily cratered landscape, lacking the broad dark plains that dominate much of the near side. This initial observation establishes a fundamental contrast between hemispheres. Later missions map the far side in increasing detail, using cameras, altimeters, and spectrometers to record elevation, composition, and surface features. Orbiters from multiple space agencies contribute to this mapping. Instruments measure reflected sunlight at different wavelengths, allowing identification of minerals across large areas. Other instruments detect gamma rays and neutrons emitted from the surface, providing information about elemental composition. Laser altimeters map elevation with high precision, revealing the depth of basins and the height of highlands. Together, these measurements create a detailed global picture of the far side. One significant step in far side exploration involves placing a lander and rover directly on that hemisphere, because direct radio contact with Earth is blocked. Such missions require relay satellites positioned where they can maintain communication with both the lander and Earth. This arrangement allows continuous data transmission despite the shielding effect of the Moon. The presence of a relay system demonstrates that far-side exploration is technically feasible, though more complex than operations on the near side. Surface missions confirm many conclusions drawn from orbit. The regolith behaves as expected, consisting of fine dust and broken rock. The terrain is rugged, with slopes, craters, and scattered boulders. Instruments on the surface analyze soil and rock composition, detecting minerals consistent with the North-Ossitic highlands and local variations influenced by impact processes. Measurements of temperature, radiation, and local environment align with models developed from earlier data. In some far-side landing regions, observations suggest the presence of materials excavated from depth by large impacts. These materials differ slightly in composition from typical surface highlands, supporting the idea that deeper layers of the Moon have been exposed in certain areas. The South Pole Aitken Basin is of particular interest in this regard, as its immense scale increases the likelihood that lower crust or upper mantle material lies closer to the surface. Surface measurements and orbital data together reinforce this interpretation, though direct sampling of deep origin material remains limited. The far side also provides an environment suitable for low-frequency radio astronomy. Because the Moon blocks much of Earth's radio interference, instruments placed on the far side can detect faint cosmic signals that are difficult to observe from Earth or near-Earth orbit. Experimental deployments and studies indicate that this environment is exceptionally quiet in certain frequency ranges. While large-scale observatories have not yet been permanently established there, the potential is well supported by measurement and modelling. Radiation measurements taken on the far side show conditions similar to those experienced in other parts of cislunar space. Without a global magnetic field or thick atmosphere, the surface is exposed to solar and cosmic radiation. Data from instruments confirm expected levels and variations, influenced by solar activity and local shielding from terrain. These findings match predictions based on physics and earlier missions. Temperature measurements also align with established understanding. Surface temperatures rise significantly under direct sunlight and fall to very low levels during the long lunar night. In permanently shadowed regions near the poles, temperatures remain extremely low, consistent with the presence of cold traps. Observations support the likelihood of water ice and other volatiles in these monarchic, though detailed distribution remains uncertain. No credible observations from far-side missions indicate phenomena that contradict known physical laws or established models of lunar formation and evolution. The terrain is rugged, ancient, and shaped by impact. The composition reflects early differentiation and limited volcanic activity. The environment is defined by vacuum, radiation, and extreme temperature variation. Where uncertainty remains, it concerns details of distribution, timing, and internal processes rather than the existence of unknown forces or structures. The far side does, however, challenge perception in a different way. It is a region that remains hidden from direct Earth view and requires indirect methods to study. This separation can create an impression of mystery. In practice, each layer of observation reduces that mystery by replacing absence of data with measured information. The progression from first images to detailed maps and surface measurements shows a consistent pattern. Each new mission confirms earlier interpretations while refining them. Exploration of the far side continues to expand through planned missions and ongoing analysis of existing data. Future efforts may include additional landers, rovers, and possibly sample return missions aimed at collecting material from key regions such as the South Pole Aitken Basin or polar cold traps. These missions would provide direct laboratory analysis of far-side materials, improving understanding of crustal composition, impact history, and volatile content. It remains uncertain how extensive human exploration of the far side will become. Technical challenges include communication, navigation, power supply during long nights, and the difficulty of landing in rugged terrain. These challenges are engineering problems rather than scientific mysteries. Solutions involve relay systems, advanced guidance, energy storage, and careful site selection. Observations indicate that with sufficient preparation, these challenges can be managed. The far side, as revealed by exploration, is not a place of hidden anomalies but a place of preserved history. Its surface retains the marks of early impact, its crust reflects ancient differentiation, and its polar regions hold traces of volatile accumulation. The findings from orbiters and landers align with a coherent model of lunar evolution, supported by decades of research. Where details remain uncertain, they are framed by data rather than speculation. In this layer of understanding, what astronauts and instruments discover is not something that disrupts known science. It is something that deepens it. The far side confirms that the Moon is a record of processes that shape rocky bodies throughout the solar system. It shows how impact, heat, and time interact to produce the landscapes observed today. The discoveries are not sudden or dramatic. They are cumulative, precise, and consistent, building a clearer picture of a world that is hidden only by position, not by unknown forces. At the deepest level of interpretation, the far side of the Moon is not important because it hides something unnatural. It is important because it preserves, with unusual clarity, the long record of how a small rocky world forms, cools, and endures repeated collision. Its meaning lies not in fear but in persistence. The far side keeps more of its ancient surface exposed than the near side. It shows what happens when early crust remains visible instead of being widely covered by later lava. It becomes a broad archive of the early solar system, written in relief, composition, and structure across nearly an entire hemisphere. The first part of that meaning concerns time. The far side contains some of the oldest large-scale surfaces on the Moon. Age, in planetary science, is not always measured by direct sample dates alone. It is also inferred from crater density, stratigraphic relationships, composition, and comparison with dated samples from other lunar terrains. By these methods, much of the far side points back toward the Moon's earliest history. When the crust is still young, and the inner solar system experiences far more frequent large impacts than it does now. The far side, therefore, preserves a landscape shaped during a formative age of planetary bombardment. This record matters because the Moon has no active weather, no rivers, and no thick atmosphere to erase surface history in the way Earth does. On Earth, ancient crust is buried, melted, folded, and worn down by plate tectonics, erosion, and biological chemistry. Much of the earliest terrestrial record has disappeared or survives only in altered fragments. The Moon offers a different condition. It is geologically quieter and more conservative. What happens there remains legible for longer, especially where later volcanic flooding is limited. The far side, with its thick crust and reduced mare coverage, preserves this record especially well. The bombardment recorded on the far side is not just lunar history, it is also evidence about the wider environment of the early solar system. Every crater marks the arrival of a body that once moved through space between the growing planets. The sizes, densities, and superposed relationships of impact structures help scientists reconstruct how intense that bombardment is, how it changes over time, and what kinds of objects are involved. This does not produce a complete census of ancient impactors, but it offers one of the clearest surviving records available anywhere close to Earth. The far side thus becomes a reference surface for understanding the early collision history of rocky worlds. Its meaning also extends to planetary differentiation, the process by which a young body separates into layers of different composition and density. The far side preserves extensive feldspar-rich crust formed from the cooling of the lunar magma ocean. That crust remains visible over wide areas, allowing scientists to study the products of early crystallization. The contrast with the near side then reveals something equally important. A planetary body does not always evolve uniformly. Heat, chemistry, and crustal thickness can vary from one hemisphere to another. The Moon shows this asymmetry on a global scale. The far side is therefore evidence that even a relatively small body can develop strong internal differences that shape its later surface history. The South Pole Aitken Basin deepens this meaning. Its enormous excavation likely exposes or brings close to the surface materials from deeper levels than are normally accessible. In this one region, the far side preserves not only ancient crust, but also clues to the boundary between crust and mantle, altered by one of the largest known impacts in the solar system. The basin stands as a record of what giant collisions can do to a planetary crust. It shows that impacts are not merely surface scars. They can reorganize thermal history, thin crust, redistribute material, and shape later geological evolution across vast areas. The far side also clarifies the meaning of absence in science. It lacks many of the near side's broad, dark Maria. That absence is informative. It points to thicker crust, lower concentrations of heat-producing elements, and reduced large-scale volcanic flooding. It shows how what does not happen can be as revealing as what does. A surface that remains pale and cratered tells a story of blocked magma, fading internal heat, and persistent exposure. In this way, the far side teaches through restraint. Its surface is not dramatic because of later renewal. It is dramatic because so much of the early record remains uncovered. Another part of its meaning lies in observation itself. The far side is naturally shielded from much of Earth's radio noise. This makes it valuable not only as a geological archive, but also as a place from which the wider universe may be studied more quietly. The same geometry that keeps it hidden from direct view also protects certain measurements from interference. In this sense, the far side links planetary science with astronomy. It is both an object of study and a potential platform for studying older and more distant signals from space. The far side also corrects a human habit of filling hidden regions with invention. For centuries it cannot be seen directly from Earth. Later, when spacecraft finally image it, the result is not a realm of impossibility. It is a hemisphere shaped by the same physical laws as the near side, though expressed under different conditions. The hidden face proves not to be separate from nature, but fully continuous with it. What changes is not the moon itself, but the amount of measured knowledge available about it. This is one of the quiet lessons preserved there. Mystery diminishes under observation, yet importance often grows. In terms of future exploration, the far side holds value because it concentrates multiple scientific themes in one hemisphere. Ancient crust, giant impact structures, radio quiet, and polar cold traps all occur there. These features make it a place where sample return, long-term measurement, and carefully planned surface operations could answer questions about lunar origin, early solar system bombardment, volatile migration, and internal evolution. The far side does not promise simple answers. It offers constrained evidence, which is more useful. It allows broad theories to be tested against old terrain that has not been widely reset. What astronauts and robotic missions discover there, when described accurately, is not terror but scale. The far side makes clear how long geological time really is, how completely impact can reshape a world, and how little of early planetary history survives on more active bodies. Its silence, its radio shadow, its pale highlands, and its vast basins all point toward this deeper meaning. It is a preserved outer shell of ancient events, still visible because later change remains limited. It is the moon's great memory surface. In that sense, the far side is less a hidden place than an exposed one. It exposes the old crust. It exposes the record of bombardment. It exposes the asymmetry of lunar cooling. It exposes the lasting effects of giant impacts. It brings into view processes that on Earth are mostly erased, beneath dust and crater rims, within the thickness of its crust and the quiet of its polar shadows. The far side holds the oldest readable pages of nearby planetary history. That is what makes it significant. Not that it conceals something waiting in darkness, but that it continues to reveal, with unusual steadiness, how the moon and worlds like it come to be. The far side of the moon remains quiet in the measured way that stone remains quiet. It turns with the rest of the moon in its steady locked motion around Earth. Sunlight crosses its crater rims and high plains, then leaves them to a long cold darkness. Dust rests over broken rock. Ancient basins hold the shape of impact older than almost any landscape on Earth. Beneath the surface, thick crust preserves the outcome of early cooling. Deeper still, the mantle and small core hold the fading record of a world that once carries more internal heat than it does now. Nothing there needs exaggeration. The terrain is severe enough in its ordinary reality. It is dry, airless, exposed to radiation, and marked by collisions that span billions of years. Yet it is also orderly. Each feature belongs to processes that can be measured and compared. The hidden hemisphere is not hidden from science any longer in the old sense. Orbiters map it. Landers reach it with relay support. Instruments read its minerals, temperatures, gravity, and faint magnetic traces. The unknown narrows, while the significance remains. In the stillness of the far side, the largest discovery is continuity, the same laws that shape planets, rocks, heat, and motion act there without interruption. Craters form, dust gathers, ice survives in shadow, and ancient crust endures where later volcanism stays limited. The result is a place that keeps old history near the surface. So the far side settles into view not as a place of fear, but as a place of deep time. It carries the pale brightness of feldspar-rich highlands, the darkness of permanent shadow, and the silent curve of a hemisphere once unseen. It remains remote, but not unreachable. It remains austere, but not unknowable. In its quiet record of formation, impact, cooling, and preservation, it offers one of the clearest nearby views into the early history of the solar system.